Hi everyone, this is lecture 31 in analog circuits. In this lecture, we will discuss two important applications of operational amplifier. The first one is operational amplifier as a differentiator, and the second one is operational amplifier as an integrator. Before we discuss these two applications, first we will see what we have discussed in the previous lecture. In the previous lecture, we have discussed three applications of op-amp. There is summing amplifier, or we can say weighted summer, then difference amplifier, and finally we have seen voltage follower. So in summing amplifier there are two configurations, that is using inverting configuration and non-inverting configuration. When we use inverting configuration, we will get the output equations like this. So we can use either a superposition theorem or directly virtual ground concept. So once we apply this virtual ground concept, we will get minus of Rf by R1 into V1 plus Rf by R2 into V2. If there are so many input voltages, we will get the Rf by R3, Rf by R4 and so on, right? So there are some weights and we are getting the summation of input, so that's why it is called weighted summer. Next, if we take Rf is equal to R1 is equal to R2, we will get simply minus of V1 plus V2 etc. we have seen in the previous lecture. Then this is the non-inverting configuration of this summing amplifier. So for this again we have to either using direct approach, that is virtual ground concept method, so finding V plus etc., or superposition theorem. So once we apply that, we will get the gain as this one, non-inverting configuration gain 1 plus Rf by R3 into, so here when I applying V1 alone, so this will become ground, so R2 into V1 by total resistance plus, if V2 is there, so this will become 0, that means R1 by R1 plus R2 into V2 and so on. So this is the again weighted summer, or we can say summing amplifier. Next we have seen the difference amplifier, or we can say subtractor. So in this we will give the inputs to both input terminals of the op-amp, and we got the output equation as, suppose if I am applying only V2, V1 is 0, then it will become minus Rf by R1 into V2. If this is V2, we are making V2 0, V1 applying, so if I apply here suppose some V plus, so 1 plus Rf by R1 into V plus, but what is V plus? So voltage division rule, V plus is equal to R3 by R2 plus R3 into V1, right? If we take these assumptions, we will get directly V1 minus V2, so that this will become as subtractor. And finally we have seen the voltage follower, so the output follows the input, or the voltage gain of this voltage follower is AV is equal to 1, right? So there are other names, that is voltage buffer or unity follower. So that's it. These are the circuits what we have discussed in the previous lecture. Now we will see two more applications of this operational amplifier. The first one is operational amplifier as a differentiator. If we observe these three circuits, voltage follower, difference amplifier, summing amplifier, we used only the resistors. If we include the capacitors or inductors, then we can make this operational amplifier to become as a differentiator or integrator etc. So we need to add a capacitor either input side or the feedback side. So if I want a differentiator, so I will take the operational amplifier like this. So I am using inverting configuration, that means the non-inverting terminal will be connected to ground. If I include a capacitor to the inverting terminal, and this is the input terminal, this is the input voltage, this is the capacitor, and I am using the feedback resistor as it is. This is the V0 and this is the RF, right? Now how can we say that this is a differentiator? For that we have to do analysis and we have to find the output voltage. Once we got the output voltage, then we can tell is it a differentiator or integrator. Now before analyzing this circuit, we need some basics about the capacitor. So whenever there is a capacitor, suppose if I want the voltage VC across the capacitor and suppose IC, right? So what is the relation between this? So we know IC is equal to C into D VC by dt, or VC is equal to 1 by C integral IC dt. One more. Suppose if I want impedance across this capacitor, so or when I convert this capacitor into Laplace domain, then we have to replace by 1 by SC, right? So first we will analyze the circuit in time domain. Later we will analyze the circuit in Laplace domain also, because we will get questions based on this differentiator. Sometimes they may ask find the cutoff frequencies for differentiator or integrator, etc. So for that we need the Laplace domain approach also. Now we'll see the analysis, how to find the output voltage. Simple virtual ground concept. Now by virtual ground concept, this is connected to 0, so that means this is also will be 0. Now I am applying the nodal analysis at inverting terminal, or at 0 volt we can say. Now how to apply the nodal analysis? So we need to find what is this current. Suppose this is I1 and what is this current I2. So the current through capacitor, so what is the current through capacitor? C into dV by dt. But there is a voltage difference. See, this is a 0 volt, this is a VI. So how can I write this one is, first I will write like this: I1 leaving, I2 is also leaving, is equal to 0, because the input current to this op amp is 0. But what is I1? So C into d by dt of the voltage difference, that is 0 minus VI. So I cannot write directly dV by dt, because there is a voltage difference between this capacitor. So 0 minus VI. See, current is flowing like this. So difference means 0 minus VI plus I2. So again, what is the difference? 0 minus V0 by RF. 0 minus V0 by RF is equal to 0. I need V0. So what I will do is V0 by RF that side. So V0 by RF is equal to minus C dVi by dt. So this will come out as V0 is equal to minus RF into C into dVi by dt. So the output voltage is the differentiation of the input voltage with some constant. So that's why this circuit is called a differentiator. Now the same analysis can be done using Laplace domain approach. So that also I will do. Please follow carefully. So when I convert into Laplace domain, C will become 1 by Cs. So this will become Vi capital minus plus, this is anyway ground, RF will be RF only, this is capital V0, this is RF. So again by virtual ground concept this will become 0. Now we can apply directly nodal analysis. So 0 minus Vi by 1 by Cs, because now it is a impedance, plus 0 minus V0 by RF is equal to 0. So what I require? V0 by RF is equal to Cs into Vi. So I need only V0. So V0 is equal to RF into, sorry I forgot minus is there, C into S into Vi. So this is in the Laplace domain, so because this is V0 of S into Vi of S. Now if you recall from the Laplace transform, suppose x of t Laplace transform is x of s, then if I differentiate x of t in Laplace domain, we will get s into x of s. Now if I take inverse Laplace transform here, so we will get V0 of t is equal to, again forward minus RF into C, this is d by dt of V of t or Vi of t. So again we will get the output voltage is equal to differentiation of the input voltage with some parameter. Now we can give another name for this differentiator depending on its frequency response. So if I find the gain, that is a magnitude, that is what is this? V0 of S by Vi of S is equal to minus RF into C into S. Now if we substitute S is equal to j omega, then it will become V0 of j omega by Vi of j omega is equal to minus RF into C into j omega. Now if I take the magnitude, if I want magnitude, Vi of j omega is equal to simply RF into C into omega. So when we plot the frequency response, this is the, you can say, gain. So with respect to omega, as omega is equal to 0, we'll get 0. As omega is increasing, suppose omega is equal to infinity, it is increasing only. but we cannot give any name for this frequency response. So generally it is a looking like high pass filter, that is low frequency signals it is not allowing, it is rejecting the, but high frequency signals it is allowing with a high gain. But practically it is not possible for high pass filter. For high, if we observe high pass filter frequency response will be something like this. If it is a pure ideal, we can get like this. So from the cutoff frequency fc or omega c, the gain will be constant. Now to make practical, so we have to modify this circuit. So how to modify is, we have to add a resistor in series with the capacitor C, right? So that is looking like this. Suppose I am adding a resistor R and this is the C. Here I am applying the input to the inverting terminal of the op amp, and there is a feedback resistor which is RF. Now if we find the transfer function of this circuit, that is V0 by Vi, then the transfer function will be looking like a high pass filter transfer function. How, we will see. So to analyze again, we will do in Laplace domain. So C will become 1 by SC. So this is anyway 0 volt. So if I find directly what is the impedance here, R plus 1 by SC, this will become 1 plus RSC by SC. Now very simple. So 0 minus Vi of S by 1 plus RSC by SC plus 0 minus V0 of S by RF is equal to 0. Now V0 of S by RF is equal to minus S into C. See, SC is going to the numerator, SC by 1 plus RSC into Vi of S. So what is V0 of S by Vi of S is equal to minus RSC by 1 plus RSC. So this is the transfer function of the high pass filter. Now how can we say this is the transfer function of high pass filter? So very simple. So there is a frequency term. So if I substitute S is equal to 0, what is V0 of S by Vi of S magnitude? See, here S is there, so 0. That means at omega is equal to 0, the magnitude or gain of this circuit is 0. Suppose if we substitute S is equal to infinity, the magnitude will be V0 of S by Vi of S is equal to, so take S out, so S will be cancelled, so this will become 1. How? So S will be common, I am taking, so 1 by S plus RC into RC. SS cancel, so infinity is here, so 0, 1 by infinity 0, so RC will be cancelled, so this is the 1. So if I draw the frequency response with respect to omega, I am drawing, this is V0 of S by Vi of S magnitude. So at low frequencies the magnitude is 0, and as the frequency is increasing it will increase, but the maximum is 1. So we have to find one more frequency, that is called omega C, that is called cutoff frequency. So what is the cutoff frequency is very simple. At omega C, V0 of j omega by Vi of j omega magnitude will be 1 by root 2. Maximum gain is 1. So but at omega equal to omega C, generally we say it is 3 dB frequency. So at a 3 dB the gain is 1 by root 2 if it is in a linear. If it is in dB, maximum minus 3 dB. So if we substitute this 1 by root 2 in this expression, then we will get the omega C or omega 3 dB. That is, so how to find magnitude? V0 of j omega by Vi of j omega is equal to R omega C by square root of 1 plus RC square into omega square. Now at omega is equal to omega C, magnitude is V0 of j omega by Vi of j omega is equal to 1 by root 2. So 1 by root 2 is equal to R omega C by 1 plus RC omega square root. Now if I cross, now to simplify, if we make both sides square, something like this. So this will become 1 by 2 r omega c square by 1 plus rc omega square. So cross multiply, so this will become 1 plus r omega c square is equal to 2 times of r omega c square. So if this is going that side, r omega c square is equal to 1, or omega is equal to 1 by rc. So here we have to substitute omega is equal to omega c. So the cutoff frequency is 1 by rc, or fc is equal to 1 by 2 by rc. So in the GATE exam, sometimes we may get questions based on this concept. So they give some circuit like this. So they may ask what is the cutoff frequency, or what is the 3 dB frequency of this circuit. So if there is a resistor here, then 1 by 2 pi r into c is the frequency here. So don't consider this feedback resistor when it is a high pass filter or a differentiator. Now, so we need to conclude one thing. How can we say that from the transfer function it is a differentiator or integrator? So we got like this: V naught of s by Vi of s is equal to minus RSC by 1 plus RSC. Suppose if RSC is very much less than 1. So what is this meaning is omega is very much less than 1 by RC. Or we can say f is very much less than 1 by RC. So what is this meaning is I can neglect this term, so that V naught of s is equal to minus RSC into Vi of s. So if I take the inverse Laplace transform, what we will get? V naught of t is equal to minus RC into d by dt of Vi of t. So if we see the frequency response of this high pass filter, where the differentiation will be happen is, the differentiation will not happen at this, after these frequencies. Where the gain is constant, it will not give any differentiation. Whenever there is a transition, see here there is a transition is happening from the gain is increasing, or we can say below these frequencies the gain is falling. So in this region the differentiation will be happened. That's why the condition we got, omega is very much less than 1 by RC. So what is omega? We got 1 by RC only. So this cutoff frequency is 1 by RC. So below this frequency we will get the differentiation. Remember this point, very very important. Alright. So as omega is very much less than the cutoff frequency, we will get the differentiation. So differentiation is possible, right? So this is about the differentiator. And the differentiator is nothing but a high pass filter. Now there is a blind rule to identify the configuration of the filter. So this is the in Laplace domain. So very simple. If I substitute s is equal to 0, 1 by 0 will become infinity. That means it will be like an open circuit. Now is there any input is going to the output? No. So V naught will be 0. If I substitute s is equal to infinity, 1 by infinity 0, that means it will become short circuit. That means the input is going to the output. So V naught is some finite value. How much we don't know, some finite value. So low frequencies output is 0, high frequencies output is finite. So that means it is not allowing the low frequencies but allowing the high frequencies. So what is this filter? High pass filter, right? So this is about the differentiator and high pass filter and how to find the cutoff frequencies, etc. Next we will see the operational amplifier as an integrator. This analysis will be as it is, no change at all, but the capacitor location will be changed. That's it. Now we'll discuss the integrator circuit. So same minus plus, so connected to ground. So here I will give some R1 to the input signal. In feedback I will use a capacitor C, and here we'll take V0. So when we analyze the circuit, the output will be integration of the input. That's why it is called integrator, and it is nothing but a low pass filter also, etc. We'll see one by one analysis. So by virtual current concept, this is 0 volts. Now so first I am doing with time domain analysis. So I1, this is I2. Now how to write the KCL, I1 plus I2 equal to 0. Now Ohm's law. Now so 0 minus Vi by R1 plus, now here what I require, I2, that is current through capacitor, but there is a voltage difference. See? So C into d by dt of 0 minus V0 is equal to 0. What I need? V0. So C minus C d by dt of V0 is equal to Vi by R1. So it is dV0 by dt is equal to minus 1 by R1 into C into Vi. Now I need V0. So what we need to do? Integrate both sides. So what we will get? V0 is equal to, so anyway this 2 will be cancelled. So V0 is equal to minus 1 by R1 into C integration of Vi of t dt. So what is this? The output voltage is the integration of the input voltage with some constant, right? So that's why it is called an integrator. Now the same analysis we can do in Laplace domain approach. So same circuit, R1 minus plus, now capacitor will be replaced by in S domain, so 1 by SC. This is V0 of S, this is Vi of S. So again virtual ground concept, 0 minus Vi of S by R1 plus 0 minus V0 of S by 1 by SC equal to 0. So what we required? V0 of S into SC is equal to minus Vi by R1. So what is V0 of S? Minus 1 by R1 into C into 1 by S Vi of S. Now we need the integration property of the Laplace transform. Same. So x of t Laplace transform x of S. So if I integrate x of t dt, what I will get? X of S by S. So if we take the inverse Laplace transform here, we will get V0 of t is equal to minus 1 by R1 into C integration of Vi of t dt. So what is this? Again the output voltage is the integration of the input voltage with some constant. Now how can we say that this is a low pass filter? Now again we have to find the transfer function. So V0 of S by Vi of S is equal to, see from this equation it is minus 1 by R1 into C into S. Again if I substitute S is equal to j omega, so the magnitude will be V0 of j omega by Vi of j omega is equal to 1 by R1 C into omega. So now if I substitute omega equal to 0, the magnitude is 1 by 0 means infinity. Suppose if we substitute omega is equal to infinity, then the magnitude will become V0 of j omega by Vi of j omega is equal to 1 by infinity. It will become 0. So that means when we draw the frequency response with respect to omega, this is the magnitude. So at omega equal to 0 it is infinity. As the frequency is increasing, the gain will fall or magnitude will fall, something like this, right? But this is not looking like a low pass filter frequency response, right? But actual frequency response of a low pass filter is something like this. Yes or no? If it is a ideal, we'll get something like this. So this is omega C, this is omega, omega C, omega. This is the magnitude, right? The maximum will get 1. But how to make this as like this? So we have to include a resistor in this circuit. So where we need to include is, we have to include a resistor parallel to the capacitor, right? So that will give the practical integrator. In the previous case, when we included the series resistance, it will become practical differentiator. Now to make the practical integrator, generally when we do in laboratories, I cannot take this circuit for practical purposes. So we have to include that resistance to make practical purposes. So now how to analyze the circuit? The same way what we have done for the differentiator. We will find the transfer function in S domain, then we will draw the frequency response, then we can find the 3 dB frequencies. So the capacitor will be replaced by 1 by SC. So RF. So here capacitor 1 by SC. I can make like this, minus plus. This is V naught of S. This is R1 Vi of S, and this is grounded here 0 volts by virtual ground concept. Now we can find the equivalent impedance here. So what is that? So Z is equal to two impedances are in parallel. So RF into 1 by SC by RF plus 1 by SC. So this will come out as RF by 1 plus RF into SC. Now nodal analysis, 0 minus Vi by R1 plus 0 minus V naught of S by Z is equal to 0. So what we require? V naught of S by Z is equal to minus Vi of S by R1. So what is V naught of S? Minus Z by R1. V naught of S by Vi of S. What is Z? Minus RF by 1 plus RF into C. So minus RF by R1 into 1 plus RF into SC. So this is the transfer function in S domain. Now what to do? So convert into omega domain. So S is equal to J omega. So magnitude I am finding V naught of J omega by Vi of J omega is equal to, I can take like this, RF by R1 divided by 1 plus RF into SC. Okay, in terms of omega, right? So J times of omega. Now at omega equal to 0, what will happen? So 1 plus 0. So the magnitude is V naught of J omega by Vi of J omega is equal to RF by R1. When we take RF is equal to R1, we will get as 1 if RF is equal to R1. Next, if I substitute omega is equal to infinity, what the magnitude will become? 1 by infinity means we'll get 0. So what is this meaning? Output voltage is a finite value. For high frequencies, output is 0, right? So that means it is allowing low frequency signals and it is rejecting high frequency signals. So when we draw the frequency response with respect to omega, so this is the magnitude. So at omega is equal to 0, we got RF by R1, and if I assume RF is equal to R1, it will be 1. So RF by R1. As it is, the frequency is increasing, the gain will falls. So at omega is equal to omega C or omega 3 dB, the gain will be maximum, that is RF by R1 by root 2. So at this frequency, we have to find the next we need to find this omega C, that is cutoff frequency or 3 dB frequency. That is below this frequency it will allow, after this cutoff frequency it will reject the signals. That is the meaning. Now we know at omega is equal to omega C, the gain is maximum by root 2. So what is the gain here? See, actually this is not magnitude. If this is the magnitude, we have to make this is square root of a square plus b square. So what is the magnitude? V naught of J omega by Vi of J omega is equal to RF by R1 by square root of 1 plus omega RFC square. Now we know at omega equal to omega C or omega 3 dB, the magnitude will be 1 RF by R1 by root 2. This magnitude RF by R1 by square root of 1 plus omega C RFC square. So these two will be cancelled, and if we make both sides squaring, then it will become 1 by 2 by 1 plus omega C RFC square. So cross multiply, 1 plus omega C RFC square is equal to 2. So this will become, see, this one is going that side, so 2 minus 1, 1. So I can directly write omega C is equal to 1 by RF into C. So when I convert into F domain, so FC will become 1 by 2 pi RF into C. So remember this formula. So we can apply directly this formula. If suppose in the gate exam they may ask, find the cutoff frequency of the given circuit. So what is the circuit? This is the circuit. So there is a capacitor here and there is a RF here. So for low pass filter, so what is the cutoff frequency? 1 by 2 pi RF into C only. So there is no relation of here this with this R1. And finally we need to discuss one point. At what frequencies the integration will be happen? So when we see the frequency response of this low pass filter, so up to this cutoff frequency the gain is almost constant, but after this cutoff frequency the gain is changing drastically. So this is the transition region. So that means the integration will be happen in this transition region only. So how can we say that? So this is the transfer function. Suppose if we assume S into RF into C is very much greater than 1, so that we can neglect this 1, then the V0 of S by Vi of S will be minus RF by R1 by S into RF into C. See, so RF cancel, this will become minus 1 by R1 into C into 1 by S is the V0 of S by Vi of S. So V0 of S will become minus 1 by R1 into C into 1 by S into Vi of S. Now if we take the inverse Laplace transform, then it will become V0 of t is equal to minus 1 by R1 into C. So 1 by S into Vi of S. So integration of Vi of t dt. So we are getting the differentiation of the input when we assume this S into RF into C is very much greater than 1. So this indicates, so if I take the magnitude, this will become omega is very much greater than 1 by RF into C. What is this RF into C? 1 by RF into C? Cutoff frequency. So when the frequency is greater than this cutoff frequency, we will get the integration. So integration of the input is equal to output voltage. Right? So remember this point. So now I will make conclusions on this differentiator and integrator. So if it is a differentiator, if I want only differentiation, so for analysis purpose, so the circuit is something like this, minus plus, this is V0 RF C Vi. So grounded, so what is the V0 will become minus RF into C into d Vi by dt. But for practical purposes this is not suitable. So what we need to do, we have to include a resistor R. This is the C, minus plus, this is the RF, this is the V0 and Vi. Then so this will be a practical differentiator. Then we have found the transfer function of this circuit, that is V0 of S by Vi of S. We got minus RF into SC by 1 plus R into SC. Right? So when we draw the frequency response, so we got something like this. Maximum we got 1. This is V0 of j omega by Vi of j omega. So and we have found the cutoff frequency as 1 by RC, or FC is equal to 1 by 2 pi R into C. So R is the resistance in series with the capacitor C here. Right? Then we have concluded that at what frequencies we will get the differentiation. So what is the condition for that? Here RSC should be very much less than 1. Yes or no? So that RSC will be eliminated. So this will become omega should be less than 1 by RC. So that means when frequency is very much less than the cutoff frequency, we will get the differentiation. So this is very important point. So differentiation. So when we are doing the practicals, so if we apply the frequency greater than this omega ct, we may not get differentiation. If I give a suppose a step function, right, something like this, as an input. If I want differentiation of this, so we should get something like this, some impulses, right? If we give the input frequency less than this cutoff frequency, we'll get the approximately like this. If we give greater than this frequencies, we will not get the differentiation. So you can verify in laboratories, right? So this is about the differentiator. Then what about the integrator? So circuit, ideal circuit is something like this. This is R1, this is the capacitor C, this is the V0, this is the Vi. So what is the expression we got? V0 is equal to minus 1 by R1 into C into integration of Vi dt. But practically it is not possible, so we need to add a resistor in parallel with the capacitor. So minus plus ground. So here I am adding a resistor RF. This is the V0, this is the Vi. Then we have found the transfer function. V0 of S by Vi of S is equal to minus RF by R1 divided by 1 plus S into RF into C we got, right? Then we have drawn the frequency response. We got something like this. So maximum RF by R1. This is V0 of j omega by Vi of j omega magnitude. Then we have found the cutoff frequency, which is 1 by RF into C. See, this is the resistance, this is the capacitance. So 1 by RF into C, or Fc is equal to 1 by 2 pi RF into C. Then finally we concluded that at what frequencies we'll get the integration? When omega is very much greater than omega c. So before this cutoff frequency we will not get the integration, but in this transition region we will get the integration, right? So this is about the application of op-amp as a differentiator and integrator. If you are having any doubt, please post a comment.